Okay, welcome everyone. We're going to get started with today's Lunch and Learn. The topic is LEED V4.1, specifically talking about the daylighting credits. So for those of you who don't know, my name is Dylan Magnus. I work for the Integrated Design Lab. We're part of the University of Idaho. We're dedicated to the education, outreach, click and zoom stuff, and technical support for high performance, energy efficient building design. We currently just hired a new intern, Isabel. She currently attends BSU. She's a civil engineering student, and she hopes to apply to the master's program. Sad to say, we will be seeing Lindsay leave. She's recently graduated and accepted a position. She's going to work remotely, I believe. But yeah, some changes happening at the lab, bringing in new students and seeing other ones graduate. So this lecture is sponsored by the Idaho Power Company. They sponsor a couple other programs that I want to tell you about. We have the technical design assistance. The IDL can provide varying levels of energy efficiency technical assistance, as well as project-based training to building industry professionals. So that's broken out into three phases. Phase one being less than $2,000, phase two being to $2,000 to $4,000, and greater than phase three, or phase three is greater than $4,000. Phase three does come with a cost share agreement. So Idaho Power will have to approve the scope of work. And then there's a cost share with Idaho Power covering 75% and the owner covering 25%. Next, we have a different lecture series called BSUG, the Building Simulations Users Group. We just had our last one for the first half of the year. So we're going on break for that, but we'll be back August 25th for automated 2D heat transfer with Grasshopper. We're hoping to have our luminaire level lighting controls installed in our office. And so we'll be adding that to the presentation list and share that with you. Then in October, we're hoping to have our previous director come back, Elizabeth Cooper, and talk about indoor air quality and energy efficiency dealing with COVID. So keep those in mind. We also have the Energy Resource Library. It's a free resource for Idaho Power customers. The library provides hundreds of free tools and guides to help you. So some of our popular categories are thermal cameras, data loggers, as well as light meters. But this year, we changed it up a little bit. Just wanted to show you some new tools we got. The focus was on indoor air quality and energy efficiency for obvious reasons. We had a spike in demand for those types of tools requests. So we got a ozone meter, O3, differential pressure, a new flow hood meter kit. It can be done by one person. You don't need two people, as well as some stronger CO2 loggers, just more tolerance and higher range. We got some smart glasses to help with remote commissioning and training offsite via remote. So now I'm going to have Cherie Wilhite from Idaho Power talk about her slides, or sorry, the Idaho Power Commercial and Industrial Energy Efficiency Program.
So I just wanted to talk to you guys briefly about, remind you about our programs. We have new construction and major renovations as well as retrofit. And we have that prescriptive program, which means it's laid out very easily. Like you do A, you get B incentive. And then there's also always our custom option. If you have a project you're working on and you don't see a prescriptive offering for an incentive, but you know there's electric energy savings, we may also be able to pay you an incentive through our custom projects. So keep that in mind on both new construction and retrofits, as well as our Flex Peak Demand Response Program. Go ahead, and I believe I have another slide as well, Dylan. We are rolling out a new program on June 15th, 2021. There is some additional measures being added. The lighting measures are staying pretty similar. The light load reduction for interior and exterior lighting is staying the same, so that isn't changing. But we are adding some new measures. We're adding an incentive for LLLC, which is exciting, as well as some other measures as well. So we're rolling that out June 15th. Now, we also have going on currently for a limited time, we have increased the professional assistance incentive. And this is for the architect or engineer that helps the owner with the paperwork to receive an incentive. That incentive used to be equal to 10% of the owner's incentive. Doesn't take away from it, it's in addition, up to $2,500 per project. For a limited time through September 23rd, so that's a year round, we started that last year in September 23rd to help increase our savings. That incentive is doubled to 20%, up to $5,000 per project. That is for final applications that are completed and turned in and paid before September 23rd. Now, I'm hoping to extend that, maybe even make it permanent, but I haven't been guaranteed that yet from my leadership. So if you have a project out there that's completed and you need to turn in the paperwork for the final application, get with me several months before September 23rd happens, because it takes some process to go some back and forth to get in all that paperwork. And I can only promise you that 20% up through September 23rd. It will go back. If it does go backwards, it just goes back to the 10%. So that incentive is still going to stay there. It just won't be as much. So reach out to me and let me know if you need some help, or you need the application, or you want to know what applications are in my system that haven't been turned in that you're the architect or engineer on. Feel free to reach out to me. And I think that's all I've got, Dylan.
Okay, thank you, Sherry. So let's get into today's lecture. Let me close and move a few things. So if you have questions, please put them in the chat, and I'll get to them as I see them. So here's an outline of today. We're going to talk about LEED V4 daylighting, but in order to want to give you some background on how we got there to the current standardization of lighting measurement. So we're going to talk about light versus daylight, a little bit of light history, pun intended, measuring light, refining the measurement of light, standardizing light measurements, and then we're going to get into the nitty-gritty fun stuff of comparing V4 to 4.1, what changes have occurred. And then I'll go into daylighting early and some tips and tricks that could help you meet the criteria or figure out which option to apply for, or to set your goals for the project. So right off the bat, light is photometry. Sorry, photometry. It's commonly referred to as optics. It is a science of the measurement of light in terms of perceived brightness to the human eye. It's referred to as optics, but optics is technically the branch of physics that studies the behavior and properties of light, including interactions with matter and the construction of instruments that are used to detect it. Daylight, on the other hand, is a combination of all direct or indirect sunlight during the day. That being direct sunlight, diffused sky radiation, as well as reflected from various objects, i.e. landform, body of water, or buildings. Typically, how we like to see it is the use of light from the sun and sky to complement or replace electrical light. So light, or visible light, is electromagnetic radiation within the portion of the electromagnetic spectrum that can be perceived by the human eye. So this spectrum is defined between 400 to 700 nanometers. And so you can see here, it's a pretty big spectrum, and we have this small little sliver that we have. Now, if you look at a lot of the visual spectrums, you're going to see they don't always agree with the range. So like, for example, the image I'm showing you goes from 350 to 750 instead of 400 to 700. So there's still a little bit of a debate on what the exact boundaries of the ranges are, but anywhere from 350 to 750 is kind of the generally accepted consensus. If we're dealing with infrared, we have longer wavelengths. If we deal with ultraviolet, we have shorter wavelengths. So getting into history of it, I'm sure you all have heard this before. If a tree falls in a forest and no one is around to hear it, it doesn't make a sound. The equivalent in the lighting industry is if light is emitted in a space but nothing is around to perceive it, does it still act the same? And we'll get into that later. So light's been around a very long time, obviously. We've been experimenting and exploring it for a very long time. One of the first documented, emphasis on documented, being the ancient Egyptians and Mesopotamians. They developed the first, what you would call a lens from polished quartz. Kind of lags there, and then we see a huge push of understanding or questioning and theorizing with Al-Zahin. Is not Persian, I'm forgetting the territory, I apologize, but he's considered the father of optics. It was in the 11th century. And he kind of proposed a lot of what was experimented and hypothesized and actually carried out in the 13th century. So we see that with Roger Bacon. He kind of gets credit for this, though there are several that have done research for this. And it's that light refracts from objects. And then later from there, we see the first wearable eyeglasses invented in Italy around 1286. This led to an optical industry in the 13th century, particularly around the Florence and Venice city-states territories. And this kind of helped this industry, this development, this standardization and understanding of how light behaves and how we can influence its behavior, led to the inventions of the optical microscope and the refracting telescope. So this is kind of important in that, I don't know why that's still there. Important because this kind of defines how the lighting value chain works. So we have the theoretical, where people are questioning the behavior of light. Why does it do what it does? Does it always do that way? What if A, B, and C come into effect? They're just questioning it. That's the theoretical part of it. That will lead into the opinions and facts, which is the formulation of hypothesis, as well as the experimentation of those hypotheses, which generally lead to a fact, which is basically a opinion that is readily agreed upon by the majority of consensus. So in that, with that, those facts or understanding of certain properties of light and how they work leads to practical applications, i.e. the microscope or the telescope, which then feeds back into theoretical to allow us to explore even further on the properties of light, as well as other areas of interest. So we kind of take a break from there, and then it's not till about the 17th century. We have Johannes Kepler. He's not officially credited as the second father of optics, but I definitely consider him to be pretty high up there on what he's done. You have the inverse square law, further explanation of why lunar and solar eclipse manipulate light the way they do. You have the retina, recognized as an organ that records that recorded images. Not entirely accurate, but he's on the right path, as well as refining the telescope. So that's when you have Snell's law and other things like that coming up, where we really figure out how to manipulate light and get it to kind of bend to our will, so to speak. Then we start getting back into the theoretical again, where we're like, what is light? Is it a wave or is it a particle? So for a while, light was considered a wave. It was kind of in conjunction with the theory that objects emitted light, was kind of the reason why that was correlated. And so, that was a pretty strong theory, but ultimately Huygens and Hooke lost that battle with Newton, mostly just due to an untimely death. So he couldn't finish the argument, so to speak. And Newton, being regarded as the physicist that he was at the time, and even now still, kind of just assumed that he was right. So for a while there, we were under the impression that light is a particle. And while that is true, it's not the whole truth. Light does experience wave properties. And so from there, we see the development of wave properties and wave optics, and that unleashes a whole new area of study for light that leads us to black body radiation and the photoelectric effect from Albert Einstein. So what does that all mean? Well, through all that understanding and those new fields and areas of study for light, we have different ways of measuring and interpreting the light. So the most common one in our industry is lumens. Lumen is a photometric unit of light output, and is defined by the amount of light given into 1 steradian by a point source of 1 candela string. Their relationships to watts depends on the wavelength according to how visible the wavelength is. Typically in America, for the commercial, residential, mostly residential, but it did bleed over to commercial in my opinion, was basically understanding light through watts. It's just kind of an American concept. But watts are a unit of radiant flux, or radiant flux, while lumens are units of luminous flux. I think it's supposed to be radiant flux, sorry. Watt is a unit of power. This power is not a measure of the amount of light output, but rather indicates how much energy the bulb will use. Watts can also be a direct measure of output. And so here's a paper I've read about, was dealing with the daylight performance in classrooms. But I really like this table that they created for explaining a lot of the different metrics that are used in assessing daylight performance. So we have 3 main categories. We have illuminance based. So obviously that's illuminance. We have the uniformity ratio, the daylight factor, UDI, useful daylight luminance, daylight autonomy, and the one you're probably more familiar with, SDA, being spatial daylight autonomy, and ASE being annual sunlight exposure. We do have luminance based. That deals with more of a glare and occupant comfort and perception of light. So spatial visual discomfort as well as contrast. And then in the other metrics category, we have the circadian metrics. That's just dealing with your circadian rhythm, how your body reacts to having a readily accessible source of daylight available to you throughout the day. Things like in the productivity, reduction in sick days, which gets into this point, which typically things get put into 2 categories in our industry. They're either energy benefits or they're non-energy benefits. The energy benefit being a measurable difference that can be calculated and used to project savings for a cost-benefit analysis. In our case, we're looking at kilowatt reduction of maintenance, and data analysis for trends. The non-energy benefits being either it's just not measurable or the unit of measure is still being debated. So here again, I have that productivity, the sleep cycle dealing with melatonin, wellness, having access to daylight and maintaining a good quality of indoor air, which has been shown to have a reduction in sick days for workers. What I don't have on here would be something like glare. That unit of measurement is still being debated in the community. But the 2 units you're probably most used to seeing for applying for code or standardization is not lumens, but rather is lux and foot candle. Lux is a unit of measurement for scientific analysis. 1 lux is the amount of light from the same source at 1 meter. It's what's used in LEED V4 and 4.1. It makes math a lot easier, to be honest with you. I'd rather do calculations with lux than I would with foot candles. Foot candles being the unit of measurement for code compliance. So 1 foot away is 1 foot candle is equal to 1 lumen per square foot. You'll see this in IEC 2015, 2018, etc. So if you want to know more about foot candle recommendations and recommended guides for space types or buildings, you can check out the Illuminating Engineering Society. Just Google IES foot candle recommendations. In addition, you can also manufacturers in like the last, I want to say 5 years or so, have begun developing their own recommendations to go with their products on what they feel the recommended light level should be for space types and how their fixtures can be programmed to meet those needs. So daylight factor, this is the kind of the original measurement value. It's the ratio of indoor to outdoor luminance. It's typically used for analyzing light uniformity. And that leads us to the useful daylight factor / illuminance. So it can be presented as factor or illuminance. Just keep that in mind. But it is the percentage of time when useful daylight is available, i.e., during building occupied hours. So what that means is, I know you all, most of you, all of you probably should though, recognize these graphics. They're from our favorite book, Sun, Wind, and Light by G.Z. Brown and McKay. So basically, that's what this does. It's giving you the daylight factor, as well. Then when you apply it to your site and your actual building orientation, that gives you the useful daylight luminance. So it's just taking the weather data from your city, your climate area, and then specifically applying it down to your site, plotting that and figuring out the angles of incidence for solar altitude, figuring out how often the sun is going to be available, whether it's it's mostly overcast or it's mostly clear, or if it's a hybrid mix of in between. That's going to help you inform what daylight strategy you want. So if you have a site where it's mostly overcast, like in this example they have in the book, St. Louis, Missouri, you can still do daylighting. You're just not going to do it in the traditional sense. So skylights, believe it or not, actually receive more light on overcast days than they do in clear days. And that has to do with the sky radiation and diffusion of sunlight from the sky to the building. There's just more available than if you would on a clear day, as well as what you get from side lighting. So why did we move away from that? Well, there's some limitations. It does not consider non-overcast sky conditions. There's no glare considerations. Typically recommends oversized windows. So, we're over designing. And then it's a static parameter. It doesn't consider time steps. So it's not, through the occupied hours, throughout the entire year, various times of day, depending on what your building occupancy is. But it is not to say that it's, worthless and, do away with it and never think about it. But it's mostly just for early design, just to kind of get you started. So you can understand where you are and where you need to go, and, how much work that's going to be. So daylight autonomy is kind of what replaced that. And so it's annual daylight metrics, but it's now referred to as dynamic daylight metrics. That's kind of mostly because people tend to confuse daylight autonomy with spatial daylight autonomy. I know it sounds weird, but they are two separate terms and they mean different things. So it's expressed as a percentage of annual daylight hours for points in a space that are above a specified illumination level. So you notice I didn't say anything about space or area or anything like that. That's daylight autonomy. It cares about the quality of light for annual daylight hours for points in a space. It doesn't care about how much area you have, what's illuminated, what's not. It's just trying to understand what is the daylight autonomy of this space or building, if you're doing a whole building. So this was first proposed in 1989. I'm not going to even try to pronounce that. It's French, I'm sorry. But it's basically the French version of the Illuminating Engineering Society. If you weren't aware, IES is referred to as IESNA internationally. But so we have that, and it really takes off and gets picked up for standardization later on, thanks to a gentleman like Christoph Reinhardt. Between 2000 and the research he did between 2001 and 2004. What's so special about this research is that it considers the geolocation specific weather data for an annual basis. So what that means is the definition of daylight autonomy was reevaluated to be measured according to defined sensors elevated above a floor area in spaces. It calculates the amount of daylight illuminance required for a specific task over occupied times of the year. Minimum thresholds were determined by IES. So basically, this leads us to the establishment of climate-based metrics for simulation, but you probably know this better as spatial daylight autonomy. In addition, climate-based metrics were supposed to set up daylighting design and analysis to be done in conjunction with HVAC energy analysis. Now that exactly didn't happen, unfortunately, but I'm hopeful that 4.1, with the changes they made, it will encourage or incentivize that to actually be a reality. Excuse me. So let's talk about spatial daylight. Excuse me, sorry. So let's talk about spatial daylight autonomy. SDA is the percentage of a space that can be daylit most of the time. It's written as this. You'll see SDA, and you'll see 300 over 50 at 55%. So the 300 over 50, it's not set in stone. What that means is that represents the minimum threshold that you're setting your lux value to. So in this case, it's 300. And then you want to know how often it's meeting that threshold. So in this instance, we want to know how often 50% of the time is it meeting 300 lux. So you'll see it expressed as 300 over 50 at 55%. What that's saying is at least 55% of the area is illuminated to 300 lux at least 50% of the time. Okay. Annual sunlight exposure, or ASE, is the percentage of a space that receives too much illumination, resulting in glare. So this is our ceiling. It's written the same way. So, but again, it has different thresholds because it's our ceiling, it's not our floor. So ASE 1000, it's 1000 lux. So that's at 13% is saying that no more than 13% of the space receives more than 100 lux for more than 250 hours per year. Okay, any questions on how those are written or expressed? Okay, real quick before we get any further, I just want to mention daylight glare probability, just so you're aware of it. DGP is an index that's used to measure glare from daylight. It considers vertical illumination at the eye level. The function of the vertical eye illumination produced by a light source, the luminance of the source, and the solid angle of the source as seen by the observer. Commonly, we don't, it's not agreed upon the actual range and what people find to be uncomfortable and what they don't, or tolerable versus uncomfortable. However, the general consensus on the best way to investigate this is through high dynamic range imaging. So I just want you to be aware of that, because that is what ASE is trying to do. It's trying to standardize that to predict when in a space there's going to be too much light and it's going to make the occupants uncomfortable. So let's get into the standardization of lighting measurements. So this is an example I like to use, LEED versus IEC 2015. If a space is considered regularly occupied, it will be considered for the LEED daylighting analysis. And I mean the entire space. So that includes the primary daylight zone, the secondary daylight zone, and the tertiary daylight zone, which is basically just the remainder of the space. Whereas IECC, it kind of has a predefined script for you to follow. So it'll basically tell you to take from the floor to the top sill height of the window, and that's your H. So how far your daylight zone will extend into the space, and then the width of your daylight zone is the width of the window plus 2 feet until you get to a full height wall or obstruction. And so that also, sorry, I gotta move some stuff. So spaces with a total of more than 150 lights of 150 watts of general lighting within side-lit daylight zones, complying with side-lit daylight zones, are required to have photo controls. So LEED doesn't really ask you about photo controls or anything like that. That's more of just the IECC side. But I just want to give you an example of how it defines its daylight zones. And so then you have top lit daylight zone, which is deals with rooftop monitors, i.e. clear stories, solitudes, and then it also deals with skylights in a particular way. But we're not here to talk about IECC, so just wanted to breeze through that. Let's talk about LEED now. LEED stands for the Leadership in Energy Environmental Design. V4 introduced the use of climate-based daylighting, spatial daylight autonomy, as a simulation-based compliance path for the daylighting credit. The reason why is SDA has been shown to be a reliable indicator of occupant perception of daylight availability. So what that means is basically 9 times out of 10, what we simulate is actually what it looks like and is perceived as in the real world. So that's why SDA has been really just such a strong metric for us to use. ASE is kind of where we get into a problem. But that deals with the Illuminance versus Luminance based metrics. So the intent is to connect building occupants with the outdoors, reinforce circadian rhythms, and to reduce the use of electrical lighting by introducing daylight into a space. I'll tell you right now, none of that is true. None of what LEED requires incentivizes you to do any of that. So I appreciate the intent, but the execution is not really there. The requirement is to provide manual or automatic with manual override glare control devices for all regularly occupied spaces. Select one of the following 3 options. So we got 3 options. And again, just to clarify, this is V4 right now we're talking about. It's simulation, spatial data autonomy, you get 2 to 3 points, 1 to 2 if you're healthcare. Option 2 is simulation, Illuminance calculations, 1 to 2 points. Option 3 is classified as a measurement, but it's still technically a simulation. It's just much shorter, single point in time. That deals, you can get 2 to 3 points for that, and 1 to 2 points for healthcare. So let's get into option 1. So here's what option 1 looks like. Probably the biggest problem I have with LEED daylighting credit is the second bullet point of use regularly occupied floor area. That is just such a broad, generic term that it literally fits almost everything in there. So that's probably my biggest problem with it. But let's get in and break it down point by point. So kind of what I define to be a regular occupied is a space within a building that will regularly have occupants within a space during business hours. Now that it can be open to interpretation and challenge because what do you define as regularly occupied? Is it people coming and going into a space frequently? Or is it someone coming into a space and staying there for an extended period of time? There's multiple ways you can interpret this definition. But typically what it does exclude are, the generic ones right out the back: mechanical, electrical, restrooms, probably get away with a vestibule, excluding that, things like that. But that's like one of the biggest cons I have is for the V4 version, it doesn't actually define or give you parameters to define what will fit into this box and what won't. So then the calculation grids, so where you're placing your sensors in the building. The grid should be no more than 2 feet apart, so you can go less. I would not recommend going less than 6 inches. It's going to be more heartache and way more computational power you want to expend than you really want to, you care to. But laid out across, again, the regularly occupied area at a work plane height of 30 inches above finished floor, unless otherwise defined. And so here's kind of what that looks like. Some of it's open to interpretation. Like you can see there's, they don't mention it in V4, but there is an IES standard called LM83 that references spatial daylight autonomy in ASE. And it gives you recommendations for placing grids and how to do that, what it recommends. Again, that's where I get that no less than 6 inches from. But here, so like I could include this row of sensors, or I could exclude them. And so that's the way you determine if you should do that or not. It comes from that LM83 standard from IES. And so for example, like this one right here, it populated sensors on here for whatever reason. So I had to go in and tell it, hey, don't include those sensors are in the wall. So, you know, just up to your discretion. Typically the 2 feet by 2 feet is enough resolution to get you an accurate picture of what's going on inside the space while minimizing computational time required for the simulation. So next, we're going to need to do an hourly time step analysis based on typical meteorological year data, i.e. your typical TMY, TMY3 weather file. And this one was more open to interpretation. You know, you could do 8 a.m. to 4 p.m. or 9 a.m. to 5 p.m. If you just, you know, explain why the building occupied hours were slightly different than what they standardized. But those are the two that I typically have been asked to use in projects. And then lastly, it wants you to include any permanent interior obstructions. Movable furniture or partitions may be excluded. And so the reason why this is important, we have our design tools here at the IDL Boise website. It's under services. So if you click on design tools, we have a handful of them, but the one I want to show you right now is a daylight pattern guide. And so if you go there, you click on patterns, and you go to workstation partitions. This is why modeling permanent furniture and partitions in spaces is very important, is because they will affect the performance of the daylight in the space, either by helping you or it could hurt you, depending on how you design and the height of your partitions. I would not recommend having any partitions above 30 to 36 inches. That's just my recommendation. If you can, you know, so that's what this scenario looks like. So basically the partition is at desk work plane height. So you still have it to divide and help define the space, but it's not hindering daylight as much as if, you know, it was open, as well as in a simulation, I can exclude these to help because the work plane height is just above it. Okay. And so what that looks like for applying for points is basically you have to achieve an SDA of 55% to achieve 2 points. You have to achieve a SDA of 75% at 3 points. Oh, or achieving a 75% will get you 3 points, sorry. Then healthcare is on the right. So option 2, Illuminance calculations. So we're going to demonstrate through computer modeling that illumination levels will be between 300 and 3000 lux for 9 a.m. and 3 p.m. on a clear sky day at the equinox for the floor area indicated in table 2, i.e. Regularly occupied floor area. So what that means is that we're going to have 2 simulations, first at 9 a.m. and the second at 3 p.m. Our sky conditions are going to be clear, and we're going to use the equinox. But we don't know if we want to use the spring or the fall. And again, regularly occupied floor area. So from there, it tells us to calculate the luminance intensity for sun, i.e. direct component and diffuse component, for clear sky conditions as follows. So it wants us to use our TMY file or equivalent. You're allowed to use your own weather data, but again, that's at your own risk. It could help or hurt you. And then we're going to select one day within 15 days of September 21st, the fall equinox, and one day within 15 days of March 21st, the spring equinox. That represents the clearest sky condition. Then from there, we're going to use the average of the hourly value for the 2 selected days. So now we need 4 simulations. So we're going to have simulations on September end day. So that's whatever day we decide at 9 a.m. and 3 p.m. Then we're going to have March on end day at 9 a.m. and 3 p.m. And so how do you decide what number n becomes? What day do you choose? Well, this is the time to pull out early design analysis or to perform the analysis now to determine if you should use the spring or fall equinox, as well as what day within the 15-day variable provided. So again, it says within 15 days of September 21st. So you can go before September 21st or you can go after September 21st. If you're using September, you're probably going to get better results before because that's the transition from summer to fall. Whereas in March, you're probably going to get better results if you go after the 21st because we're transitioning from winter to spring. And so that kind of deals with that. And so what that table looks like for scoring, you'll notice that it's not 55% now, it's 75%. It's a really high bar to meet that. And then for 2 points, and to get 3 points, it's going to be 90% is the average you have to get of the floor area being between 300 lux and 3,000 lux for 9 a.m. and 3 p.m., the averages of those. Then option 3, basically achieve illumination levels again between 300 lux and 3,000 lux for the floor area indicated in table 3. So again, that's dealing with the 75 and 90% of regularly occupied spaces again. With furniture, fixtures, and equipment in place, measure luminance levels as follows. Measure at appropriate work plane height during any hour between 9 a.m. and 3 p.m. So again, that's the 30 inches. Take one measurement in any regularly occupied month and take a second as indicated in table 4. So this option gives us a lot of freedom. One could argue too much. It gives you too much options, so you have too much, therefore you have a lot more data to deal with and to analyze before you figure out which one actually works for you. It also gives us some flexibility on our grids. So for spaces larger than 150 square feet, we can take measurements on a maximum 10-foot square grid, so up to there, so instead of the 2 feet. This option allows you to increase your daylight autonomy by reducing the overall amount of sensors used in calculating illumination. For spaces less than 150 square feet, or smaller, sorry, take measurements on a maximum of 3-foot square grid. So again, but just to clarify, more sensors increase the amount of time required to run a simulation, but also can make reaching the benchmark more difficult. So there's a lot of variables, a lot of sliders, so to speak, to play with and figure out how they're going to affect your building. And this is what the table looks like for scoring. So you need, again, the 75% for 2 points and 90% of your area for 3 points. And what it's talking about when it says your first measurement, any hour of any day in the month from the first table, or not any hour between 9 a.m. and 3 p.m., sorry. So let's say we choose May, because May is a good month. We know from our basic annual simulation that May performed better than all the other months. So we're going to choose a day in May for our simulation. Then for our second one, we have to choose somewhere between September and January. So that's what that means. Are there any questions so far? That was me just kind of giving you the overview of V4. So if you have any questions before we get into what's changed, just let me know. Okay. So the intent hasn't changed, as well as the requirements. Still ask to provide manual or automatic with manual override glare control devices for all regularly occupied spaces. So one of the things I liked about 4.1, the changes they've implemented, was it lowered the bar and gave different tiers that you can apply for. And probably the biggest one is that you're allowed to not really exempt, but appeal for an exemption for if a space should be regularly occupied, i.e. if it should be included in the area calculations for your daylight performance. So those are the big changes that I've liked that they've done. So we're going to go through some of those. So right off the bat, you can see that now the point structure is more broad. So we have 1 to 3 points across the board. Healthcare remains the same and was added to option 2. So let's go into those. So option 1 for, again, this is LEED 4.1 now. Perform an annual computer simulations for SDA 300 over 50%, an annual sunlight exposure 1,000 for 250 hours, as defined in IES LM83-12. So there was an update to LM83. It's now -12. You can have that. Yeah, it's on this slide. Healthcare projects must use each regularly occupied space located in the perimeter area determined under EQ credit quality views. I'll tell you right now, I mentioned healthcare a little bit. I'm on the detail for it. The reason being is you should not be daylighting your hospital. The only 2 space types in a hospital, in my opinion, that should be daylit are the lobby and the patient recovery room. Now, as said, exemptions can be made. Say a medical facility is for, rehabilitation, things like that, of that nature, where there's not, actual procedures or anything like that. So like retirement homes, those healthcare project types. You should be considering for daylight, but definitely not hospitals. Additionally, calculate the average SDA 300 over 50 value for the total regularly occupied floor area. For any regularly occupied space with ASE of 1,000 over 50, greater than 10%, identify how the space is designed to address glare. So probably the #1 culprit for projects I worked on in the past 2 years on why they would meet the SDA requirement, but ASE would throw a wrench into the accreditation plans. So it was really hard to meet both of those standards. The bars were set really high. And the problem with ASE was that it didn't take into account shading control strategies. So with 4.1, it does. You can identify how the space is designed to address glare. That can be anywhere from, a paragraph description explaining what you're doing to having a diagram, i.e. like a section of your window diagram, showing the overhang or showing the roller shades, and as well as, the angle of incidence for solar radiation. So like winter or, the spring versus the fall equinox, how you're dealing with the summer versus the winter sun, things like that. So it actually allows you to do that now. If you're curious, the LM83-12 guide is available. It's $25 for non-members. You can get it from the IES store. Before you go out and buy it though, it's for people who will be running simulations, i.e. if you're using Radiance, Honeybee, HEI 32, DaySim, etc. So if you're not actually going to be performing simulations, you don't need this guide. What it does is it defines the ranges and additional options for simulation parameters. So that includes, but not limited to, period of analysis, illumination threshold analysis area, planes and shade operations, as well as optical properties for those, interior surface reflectances, furniture and partitions, etc. So it's a great resource if you are performing the simulation, and I would recommend picking up a copy. But you don't need it if you're not actually going to be running the simulation yourself. LEED kind of provides you with all the standards. It's just that IES is the one who came up with SDA and ASE, and so they're ones that maintain it. And so this is their recommendation for how to implement that for simulations. If that makes sense. So continuing on with option 1. Again, the grids haven't changed. Hourly time step hasn't changed. You're still including any permanent interior obstructions. Movable furnitures and partitions may be excluded. And so we have this, it says CS only. If finishes in the space will not be completed, use the following default surface reflectances. 80% for ceilings, 20% for floors, and 50% for walls. The only one I disagree with on that one is the walls. My typical default is 60 to 65% that I'm running. But my default is 80% for ceilings and 20% for floors. So those are good recommendations. And assume that the entire floor plate, except the core, will be regularly occupied space. So this is kind of early design, kind of give you an idea of what parameters to be using. Or if basically you don't know what the final material selection is going to be while you're performing or filling out your LEED accreditation, you know, the wonderful Excel sheet that we all know and love. And so what that looks like, the table for applying for points, is so you want an average STA of 300/50 value for a regularly occupied floor area at least 40% of the time, or not of the time, sorry, of the area. That will get you 1 point now. So I really like that they lowered that. I kind of wish it was 30 to 35, to be honest. But that is definitely, in my opinion, a step in the right direction, you know, to start getting projects to acknowledge daylight again. The second one is at 55%. That's still going to get you 2 points. And then the third one being 75%, that's going to get you 3 points. And now, if each regularly occupied space achieves the SDA of 55%, then you're going to get an exemplary performance of 1 additional point if only 1 or 2 points achieved above. So, you know, say your whole building didn't get 75%. There were a few spaces that, you know, just didn't meet it, but your average was around, you know, 55%. Well, I mean, that's not a bad daylight design. You just didn't make it to the next tier. You shouldn't be punished for that. And so that's what this new row in the table of scoring points does. So option 2, perform computer simulations for Illuminance at 9 a.m. and 3 p.m. on a clear sky day at the equinox for each regularly occupied space. So again, that hasn't changed. A lot of this for option 2 hasn't changed. One thing that has changed is the last bullet point. Spaces with view preserving automatic with manual override glare control devices may demonstrate compliance for only the minimum 300 lux illuminance level. Okay, does that make sense? It's a very important one. That will allow you to makes this option so much more viable and not easier to obtain, but just, you know, it's obtainable now, whereas before it didn't really seem attainable. And so what that looks like is 55% is going to get you a point, 75% is going to get you 2, and 90% is going to get you 3. So again, just adding another tier so that you can more readily make that level for compliance. So continuing, again, all this has it hasn't changed from 4 to 4.1. You're still gonna use your typical TMI file for meteorological data. You're gonna select a day, 15 days within September 21st or March 21st. You're going to exclude blinds or shade from the model, include any permanent interior obstructions, movable furnitures, and partitions may be excluded. And then assuming the following default surface reflectances, if finished in the space will not be completed. Again, that's the same from option 1 that's carrying over. So option 3, again, it has the same exemption in it, which is spaces with view preserving automatic glare control devices may demonstrate compliance for only the minimum 300 lux illuminance level. So, and the other thing that changes, if you don't remember, that's why this one is considered a measurement option instead of being labeled properly as simulation, is because you're taking 4 different measurements throughout the year. And so that changes in this point distribution. So it's now 55% at one time in the year. So you can apply just for 1 point. You don't have to go for 2. But if you want to go for 2, then you have to do it has to be 75% at 2 times in the year, and then 90% at 2 times in the year as well. We'll get you 3 points. So again, this pretty much stay the same, except for these bullet points. If pursuing 1 point, take 1 measurement in any regular occupied month. If pursuing 2 points, take 2 measurements, 1 measurement in any regularly occupied month, and take a second as indicated in table 4. Grid calculations and spacing stays the same. So basically, if you only want to apply for 1 point, you would just take a measurement from this column. But if you want to apply for 2 points, you're going to take a measurement in this column. As we said earlier, we chose May, so let's choose May again. We would take it from there and say we get a point, but we feel pretty confident that we can apply for 2. So then we're going to take our second measurement here. That could get us 2 points. So option 2 and 3 become a lot more viable with this this phrasing right here. And then option 1, the bar got lowered, but in a good way, in that it needed to be lower. There needed to be more tiers of acceptance for the quality of a daylight design. And so, what option should you pursue? Well, again, this comes back to early daylighting design and analysis. So again, this is where having that early analysis on how the sun is in the climate is going to behave on our site, as well as to the building level. That will help us inform which measurements we should be taking and when, for say if we're pursuing option 3. However, what I like to do for a project that comes to me and says, hey, we're interested in doing LEED and we want to apply for it. First thing I do is I break out the calculator and an Excel sheet and I do some math. What's the area of the building? The daylight harvesting area, that's not area that I'm defining as a designer that should be daylit and has photo controls in it. That's what IEC defines as it. So that's what the daylight harvesting area line is. And then I look at what LEED is going to consider for the daylight area. Okay, and then we run the numbers. I can also break it down by individual spaces. And then, we run the numbers and say 75% of your total area. Say we're going to try to get you to 3 points, the maximum overall. You're going to need 8,450 feet to be daylit at 300 lux for at least 50% of the time, which is about 1,600 hours. So it's quite a bit. And then, I'll run through and here's 55% of it, or say you only want to apply for the first floor or just the second floor, or, know the differences to see which floor needs to have adjustments to it. I'll give you those numbers as well. So you just have an idea of this is the amount of area that needs to be daylit. Is it actually feasible or possible for us to do this? How much is it going to take us to invest in this to achieve it? And so, one of those ways, you've heard me speak in the last year. I've definitely made it known that I'm all about parametrics right now. So one of those things you should do in early design is parametric analysis, i.e. just creating multiple versions of a model and figuring out what's going to work, and combining those with other iterations. So this is an example of determining. A gentleman took the most typical space types of schools, and he basically just played with the parametrics of it, of window to wall ratio, orientation, etc. Being told I'm talking too long, I apologize. We're almost at the end. Just bear with me for a few more minutes. I like this study from this paper. They basically take all of kind of the lighting measurements or units that I've been talking about. So illuminance uniformity, STA, UDI, etc., and plotted them against different strategies he was using. So you have the base case, then the base case with light shelves, base case with light shelves and blinds, electromagnetic glazing, that electromagnetic glazing plus light shelves, reflective glazing, and just kind of compare them all across. And the reason why that's important is for this credit, the integrative process. So what that basically wants you to do is talk to your fellow engineer or talk to your fellow architect, please. And so it wants you to investigate early design concepts. And a lot of what I talk about for daylighting analysis and early design investigations deals with these in bold. So what you're looking at for daylighting is also applicable for HVAC analysis and spatial arrangement and occupant comfort and vice versa. And so in addition to doing that and preparing you for achieving daylighting credit or informing you whether you should try to apply for it, you can get this credit as well as doing work that you were already going to do to meet, your ASHRAE 90.1 standard, or showing performance above the baseline that is required, etc. So I definitely encourage you to revisit daylighting as a potential concept for your buildings using 4.1. It's still not it's not easy, but it's also not impossible anymore, if that makes sense. And so I just want to leave you with these thoughts. I'm going to launch a poll right now. I'd appreciate if you could fill that out. What's that? But basically, a few quotes. The art and science of daylighting is not so much how to provide enough daylight as how to do so without its possible undesirable effects. In addition, good daylight design should contemplate the use of several different metrics in order to gather information about all possible daylight effects. And I can't emphasize this enough, consider climate first, okay? That should always be the first consideration. And after that, I recommend looking at the parametric analysis or parametric variations, or however you want to frame it, of just building characteristics. So whether that's the room, the geometrical layout, as well as orientation or features such as depth, facade characteristics, etc. So just keep those in mind. If you have any questions, I'll take those now. I apologize for going over.